Welcome back again, and we can discuss the pipe and filter architecture. Now, this is the last architecture in my slides, but it is not the final architecture. There are many different architectures, as I told you, and I cannot go through every single one of them. What I do in here is that I show you the most popular ones that are being used in the industry, or at its core, these are the architectures that we care more than the others, I would say. So this is why we are spending so much time on these ones, but please be aware that large systems do not fit into one architecture only anymore. And just because I list these ones doesn't mean that these are the only ones available out there. There could be more, and it's just that these are the ones that I come across based on my personal experience. Okay, at the end of the day, this course is not about theory, it is about practices. And I think every single software engineering course should be taught by people that are involved in the industry or one way or another, because these are basically practical solutions, okay, that will give you some perspective on how businesses work out there. So when we come to the pipe and filter architecture, one of the keywords here is to remember that this architecture is particularly for embedded systems. It is perfect for embedded systems, and that is why it is designed for that. When I say embedded systems, I mean that the system itself is actually implemented, the software itself is implemented into the system. It is like they are complementary to each other. They are like part of each other, and they are specifically designed for it. A good example to this is the iOS for Apple phones. Now, when you look at the Android OS is not specifically designed for a phone. It is designed for a range of phones or devices to run, from smartwatches to tablet devices to many different phones. They use different versions of Android to do different stuff. It's a excellent customizable software, but it is not exactly an embedded system, I would say, although being a very system operating system, but it is not particularly an embedded system within itself, because it's like very flexible to the phones. It is that is its purpose. But when you look at the iOS, there's a big advantage there that Apple has, because they are only going to make this software available to their own configuration. And because they produce or use the hardware, so they know exactly what kind of hardware being used. They know exactly where this application would run. It's not going to be any available in any other platform that they offer. So they have a big advantage to this. So in those kind of situations where you know the hardware, you know how the system would run on that specific hardware, it is possible to use a pipe and filter architecture. It comes from the original Unix systems, where it is possible to link the processes using pipes. Okay, the pipes were basically text streams frequently used with Unix commands, which then basically used to control the Unix shell, which is the core of their operating system. The entire workflow of this architecture is surrounded with the idea that the statements, every single one of them, is actually filtered through a pipeline, which are the link processes. Okay. When we go to the pipe and filter architecture, it is impossible to omit the fact that it is used with embedded systems mostly, where you know the hardware structure and you also are aware of the software. So it is like they are working on one another. And we know a diagram. If you remember, when we saw the UML design, we mentioned that the state machine diagrams is very event state based. It shows events or responses of the systems, and is very much used with embedded systems. And we even solved a microwave question, remember? and I uploaded that to Moodle later, and we showed how a microwave works. So when you look at a microwave, it is actually an embedded system because microwave has a timer, it has a buttons on it you press and it heats your food, and there's a software behind doing that, and the software itself is particularly designed for that hardware. So pipe and filter architecture works perfectly with embedded systems, so it does actually being displayed with state machine diagram. So the UML diagram, you're going to use this type of architecture. Instead of using a DFD, you can actually use a state machine diagram. The data is processed in what we call as batches in this type of architecture. The pipe and the filter architecture is in a batch sequential model for data processing, which means the data is being sent through patches and it is done sequentially, not in parallel. Okay, most embedded systems work sequentially. So you need to complete one task in order to do another. The architecture of an embedded system can be organized as a process pipeline, which are the link to processes. If you remember, we mentioned this upstairs, that it is possible to link the processes using the pipes. And the architecture of an embedded system can be organized as a process pipeline. In other words, pipe and filter architecture is often used with embedded systems, and it is displayed with the state machine diagram. There are many examples that we can give in this category. Any kind of device that you use, such as a calculator, that the software is implemented specifically on it, is an embedded system. But these are not the limitations. There are, of course, many automobiles, medical equipment, cameras, airplanes, even toys can be counted as embedded systems. They are usually designed to solve only a few very specific problems that are not meant to change easily. This is why most embedded systems are not frequently updated. Our microwave do not ask us to update itself, because what is going to do? It's going to, we have another device to make the food cold. We call it the fridge, and the microwave is basically the opposite of it. So we do not expect anything other than heating the food when we buy a microwave. There could be some gadgets here and there, of course, but more or less that is the main functionality. The same thing goes with the fridge, toys, medical equipment, basically any industrial machine is more or less is the same. So like I said previously, embedded systems are not meant to change as often as other technologies we listed in this course. 20 years ago, if you bought a calculator, if you could travel in time and buy a calculator from 20 years ago, it's not going to be so much different than what is being sold in the shops as a calculator. It's going to do more or less the same. There could be here and there some gadgets that they added, but the calculators that we use today are the same kinds of calculators basically as 20 years ago. This is one distinct feature of this type of systems. Unlike the other architectures that we listed in this course, embedded systems are not meant to change often. They are very specific systems that designed for a very specific purpose. When you buy it, you just satisfy that condition, like microwave heating the food, fridge making the food cold, calculator doing mathematical equations. You do not expect the calculator to do translation for you from English to whatever language. But in here, there's the purpose is very specific, very focused. But when we look at other systems like our phones, while we can count the operating system behind as an embedded system and its functionality at its core is the same, it is rather a platform. So what we can say about embedded systems is that the operating system on a specific phone can be an embedded system, but the phone itself is not, because the phones are being developed so much today to do more and more stuff. Embedded systems are usually designed with pipe and filter architecture since the architecture provides a fixed structure and similar to embedded systems. So what we know from this is that the pipe and filter architecture is easy to understand, support, and reuse because what it does is that the data is always handled sequentially, uh, while there is some parallel working. I don't see many examples. Most of what I see is that these kind of devices, they perform things sequentially. Okay, so they do not wait for one another. It will, for a microwave for example, to heat the food, you need to basically finish one in order to start another. The same goes for a calculator and so forth. So at the background, it can of course do something, but it's not like the concurrent flow that we mentioned in the activity diagram. It's not like multiple threads running and completing a task. Simplicity of this architecture is probably one of the key issues that forms it. So it's like you know what the system is going to do, you are very focused on it, and you're not going to update it, which is like the perfect software that we want to develop. We don't have to worry about the requirements being changed. We know that when we complete it, our needs are very well refined, their requirements are not going to change. Perfect. So this kind of architecture is one of the few architectures that work very well with planned development rather than agile. It is pointless to use agile development in pipe and filter because requirements are not going to change. You know them. You know how a calculator is being gonna be developed. It's gonna be same as 30 years ago, and the needs are there already very well refined. We do not expect anything more than that. It's not gonna change in 5 years. It's probably gonna be the same calculator. So it's very focused and it is not going to change. Hence, this gives some advantages. There are, however, some disadvantages, as in all uh, architectures we mentioned in this course. Embedded systems, first of all, are not meant to be complicated. They have a very specific task. Although simple textual input and output can be presented this way, the graphical data can be too complicated IO formats, inevitably making it difficult to translate this into a form compatible with pipe and filter architecture. What does it mean? It means that the data will not always be cascaded into a machine readable form because the machine will not understand it. This goes against everything we mentioned in the MVC. The entire point of doing MVC is to omit the device that is being accessed and keep the data organized and just remodel the data to show it. Now in here, the system is such a simple system that it doesn't actually differentiate a mouse click from a touch. So for it, the construction of the structure, the actual action is the same. The data will always be needed to be cascaded into a machine readable format so that the embedded system can understand it. This creates some sort of complication. A CPU cannot differentiate, for example, a mouse click from a menu selection or a button click from a voice command. They are all the same to the CPU. And for an embedded system, this might create you some problems. So it goes anything against what we mentioned in the MVC. Some architectures here, such as client server, can be combined with MVC, and that can be combined even with layered architecture. But some architectures do not like each other. As you can see from this example, pipe and filter will never actually work with MVC because they simply not meant to fit together. The purpose of a CPU is to process data at the machine level, not to differentiate where the input comes from. And hence, because these kind of systems are usually developed with low level languages rather than high level languages, it could be difficult to model the data to display to the user. So if you focus on designing a specific system as a touch design, it might be difficult to support the same feature with the mouse click. It's supposed to make it available to other platforms to model the data. And this goes against everything in the embedded systems, because the embedded systems are supposed to be simple, one task or multiple tasks, but doing them in a sequential order. So just to summarize in this course what we have done, I said the lecture will be short, but we are almost 80 minutes now again. So what we want to I want to discuss today is that a software architecture is a description of how the software systems are organized. An architectural design pattern that we mentioned, some of them they work with one another, some of them do not. But these are the most popular ones I see in the industry. If I omitted any crucial architecture pattern that should exist in this slides, please let me know and I'll be happy to include them. But these are the ones that I come across, especially in the book and other software engineering resources. So these are model view controller. We mentioned MVC. Layered architecture, you use this one in object-oriented programming class. Client server, particularly for distributed systems, something I think Devri Moja covered in his network course. And finally, we discuss a little bit about pipe and filter, which are the embedded systems. So by completing this slide, I finished everything around this chapter. So if I go back, I think I only have one more chapter left. Yes, system implementation is my last chapter. So I'm gonna open this chapter in here and make it available to you now. You can have a look to it. This is a relatively short chapter. It's not very long, and we're gonna cover it not the next week. I think next week is a holiday, right? Again, a public holiday. Today is a public holiday actually. Today is the Youth and Sports Day in Turkey, but I still did the lecture despite being a public holiday. And this is the final chapter that I want to cover. So I want to open my calendar in here so you can see. I don't know if you can see it. We have like 1 week next week, public holiday. The week after, on 2nd of June, we will have a class, and I will cover this chapter, and I will also discuss a little bit more about your final exam. And you will take your final exam sometime after the 5th of June. Okay, so up until 5th of June, we have classes officially. And after the 5th of June, starting from the next week, let's say 8th of June, you will have your final exams. My final exam will be online. I think most of them will be online anyway. But my one will be multiple choice. And like I said, you don't have to memorize anything, but you need to understand in order to be able to answer the questions. You will have 20 questions in your final exam, and they will be shuffled. So your first question will be different than another person's first question. Even the options will be different. And the question will be sequential, which means once you skip the question, you won't be able to go back. Now, Tara has a question, I think. She raised your hand. You can talk if you want. Yes, you have a question?
Yes, Doctor. My own question about the pipe and filter architecture. The number of pipe and filter, it is different from one system to another system or not? If it is different by increasing the number of pipe, it does not affect of the performance of the system?
It does affect, but it all depends on what you want to design at the end of the day. Like one of the things that you should know about pipe and filter, this is a very established design. So there's nothing new to there, like more or less. So this is probably among the architectural models is the least one that is open to change. So everything here is very well defined. Everything is very well established. Your requirements are known precisely. So there are no new features that you want to basically apply. So assume that you want to work in a toy factory and you are being hired to design the interface for that toy. What they know about the toy and how is that going to function is basically very well defined to them because they know which hardware they're going to use, you know. So it's like this is an architecture where the hardware and software is being produced at the same time, and that hardware is going to basically support the software, and the software is not going to be available other than the hardware itself. Does that make sense? So if you run into a problem about performance, like in your question, you can always go back and change the hardware because you are using the hardware yourself. So performance is not a big deal. You understand? The reason why Apple, for example, uses less configuration than the Android phones is because they don't need it. They know they are using this specific software that they think that whatever gigabyte RAM is enough for them for their operating system, and they want to earn money. At the end of the day, they are just doing this as a business. So the more hardware, the more expensive hardware they put there, the more it will cost to them. So what they want to do is to reduce the cost and earn more money. And that is why performance is not a big deal in embedded systems because you are the one producing the hardware or using it. Does that make sense? So it doesn't matter if the hardware is not enough for the software because you can always go back and change it. The software is not going to be available in anywhere else. Does that make sense?
Yeah.
Very good.
Yes.
Thank you.
Thank you very much, Doctor.
Thank you for the question. Any other one?
Thank you.
Is everything clear, guys? This is one of the last meetings. I'm sad that I'm not going to meet you every week now. I hope you feel the same way. Do you want to ask any questions to me, or do you want to say anything? Okay, I guess no one wants to say anything. So I assume everything is clear now. Like I said, I put the date in here that we don't have any lecture next week because there's a public holiday in Turkey. So I'm not going to do any lecture next week. The following week, we're going to meet again, and we are going to discuss about our very last topic, which is chapter 8, system implementation. And I'm going to explain the procedure to you in terms of the final exam even more. Some examples I unlocked this week, you can see them in here, the solutions that I did in the previous years and some study questions. I think if you repeat these chapters a couple of times, read them, you'll be more than ready to the final exam. I assure you it's not going to be that difficult. Maybe the time will be an issue, but I will try to arrange that one as well. Thank you for all coming every week to my class patiently, listening to me, even with the pandemic situation. I know that some of you are in difficult situations. It's not very easy for you. I am aware that mentally and psychologically you are tired in lockdowns and you probably suffered a lot because of these situations. I really apologize for this, but I did my best throughout this term to deliver the course as efficient as I could. I tried to deliver the course close to a classroom experience. I hope you are happy about the course. I hope you have learned some stuff from it, and I hope you're going to carry this knowledge with you in your upcoming career. Thank you all for your contribution. Okay. I'll see you guys in the next weeks. Once again, take care.